Hi students, welcome to another session of All Force e-learning program. Right? In this session we shall now take up some examples, some important questions, previous entrance questions based on the topic of electric field due to multiple charges. So today's our topic is applications of electric field due to multiple charges. Applications of electric field due to multiple charges. Yes. Now, based on this one, let us take up the first example like this. First one, a very beautiful example. Three charges. Right, this question was asked in many of the entrance examinations in India. Right, very important question. Three charges are placed on the vertices of a equilateral triangle. Three charges are placed on the vertices of an equilateral triangle. Identical charges. Let's take plus Q, and plus Q. Three identical charges are fixed on the vertices of a equilateral triangle of side A. Now, he is asked you to find the electric field due to these combination of charges at different points. He may ask you to find, simple. In this one, the simple thing is, find the electric field at any of the vertex. First question. Second, a bit difficult. Find the electric field at the centroid of the equilateral triangle. Second, a bit difficult. Third, find the electric field at the midpoint of any side. So this way, the question, same thing at different points. Let us evaluate, do it carefully, right? Now, first question, let us take the first question. What is the resultant electric field at any of the vertex? Our first question is, the resultant electric field at any of the vertex. Let this be an equilateral triangle ABC. Now we are finding the electric field at C, the point C, any of the vertex of the equilateral triangle, right? All are like charges and of same magnitude. Then what is the resultant electric field at this point? Is it? So therefore, first, I was telling you, whenever you are asked to find the electric field due to multiple charges, first step, considering each charge as an isolated point charge, find the electric field due to each charge separately, magnitude and direction. For Q1, E1 bar, Q2, E2 bar, Q3, E3 bar. However, let me be any number of things. Find the electric field due to each charge separately, magnitude and direction. First step. Second step, apply the principle of superposition. The resultant electric field intensity is the vector sum of all the individual electric field intensities, considering all of them simultaneously. So here also we are going to do the same thing, right? First step, let me find the electric field intensity due to all the charges separately, considering them as an isolated point charge. Now, so I am asked to find the electric field at this point. See, first thing, very important. At this point, the charge at this vertex itself will not produce any electric field. So I was telling you, any point charge, any charge will never produce any field, it will not show any effect at itself. A charge never shows any effect on itself, right? It doesn't produce any electric field at the point where it exists. So the field produced by the charge at this point, at the point where it is existing, it is zero. So field due to C, the electric field due to the charge at C is zero. So we are finding the electric field at C, and the field due to C here at this point, zero. A charge never produces any field at the point where it exists, right? It will show the effect at other points in the field except the point where it is existing. And also the electric field due to any point charge at infinity is also zero. At the point where it is existing, no effect. At infinity it is zero. At all the other points around, it has some effect, some impact. So first, field due to C here is 0. Now let me find the field due to charge A. Charge A. Charge is a charge at point A. Charge is Q, positive charge, and the distance is A here. So forget this charge. Now I have to find the electric field at this point C. According to the definition of electric field intensity, it is the force experienced by a unit positive test charge. So to find the electric field, let me imagine a unit positive test charge. 1 coulomb positive test charge. Positive charge. Now, so I have to find the electric field due to charge at A. This is also positive charge. This is positive test charge. This positive charge repels this charge. So the force experienced by this positive test charge, it is repulsive force. So therefore, force due to this charge is away. So the force experienced by unit positive test charge is electric field intensity. So the field intensity due to A, this is EA. So EA is in this direction and the magnitude 1 by 4 pi epsilon naught. Electric field due to a point charge 1 by 4 epsilon Q by D square. So the charge is Q. It's Q by the distance of the point is A square. The direction is away from the charge like this. So first, electric field due to the charge at A. Electric field due to A is 1 by 4 epsilon magnitude of the charge by distance square. Magnitude of the electric field. Direction, since it is positive charge, when I imagine a unit positive test charge, positive repulsion, like charges repel. So the repulsive force. The electric field will be in the direction of the force. So it is in this direction. So it's 1 by 4 epsilon Q by A square. First one. Forget A, come to B. The electric field due to charge at B at this point. Again, to find the electric field, it is the force experienced by unit positive test charge. So if I imagine a unit positive test charge here, 1 coulomb charge, then this is positive charge, this is positive test charge. So this positive test charge is repelled. So positive test charge will experience a repulsive force due to the charge at B. So therefore, the electric field due to B, this is equal to formula 1 by 4 pi epsilon Q by D square. Charge is Q by the distance is A, it is A square. Distance is A square. So first step, find the electric field. We are given totally 3 charges. Three charges A, B and C. First step, find the electric field due to A, electric field due to B, electric field due to C. So electric field due to A, the magnitude is 1 by 4 pi epsilon Q by A square. Direction, since it is positive, away. Direction is away. Then electric field due to B, magnitude 1 by 4 epsilon Q by A square. Direction, away. So it is the direction. How about, there was actually charge at C, but you know, no charge will produce any electric field at itself. It shows the effect on the other charges, not on itself. So therefore, the charge that was there at C has no electric field at the same point C. So the electric field due to C is 0. That is already we have noticed. So this has no magnitude, forget about it. So there are only 2 charges, 2 electric fields, 2 vectors. Now I have to find the resultant of these 2. Coming to the second step, the resultant electric field intensity at a point is the vector sum of all the individual electric field intensities. So the resultant electric field E resultant, it is EA bar plus EB bar plus EC bar. These are the 3 things there. But EC anyhow it is 0, it's a null vector, forget. So therefore, resultant electric field is field due to the charge at A plus the field due to the charge at B. Vector sum of the individual electric field intensities E and EB. Vector sum. How do you add vectors? The vector addition of vectors is done by parallelogram law of vectors. 2 vectors A bar and B bar represented as 2 adjacent sides of a parallelogram like this. Then the resultant is given by the diagonal. The diagonal passing through the point. This is the resultant. Magnitude of the resultant are root of A square plus B square plus 2AB cos theta. So the vectors are A and B, theta is the angle. Now here our individual vectors are EA and EB. So the resultant will be root of A square plus B square. So that is EA square plus EB square plus 2AB. So 2EA into EB cos theta, cos of the angle between the vectors. Listen. But you know, we are given with an equilateral triangle. In an equilateral triangle, all the sides are equal and all the interior angles are equal. So therefore, this angle is equal, and we know this is 60 degrees. In an equilateral triangle, the angle at the vertex 60 degrees. So if this is 60, now this is vertically opposite angles. If this is 60, even this is also 60. Now completing the parallelogram. If I complete the parallelogram, this is the parallelogram, right? So these are the individual vectors A bar and B bar. This is the parallelogram. Then the resultant is given by the diagonal. This is the resultant electric field. The resultant vector is given by the diagonal passing through the point of vectors. So this is the resultant electric field. The angle between them is 60 degrees. So this, if I consider this as A, this as B, this as R, then R is root of A square plus B square plus 2AB cos theta. So therefore, resultant electric field, magnitude of the resultant electric field is under root of EA square plus EB square plus 2EA EB into cos theta, cos of the angle between the vectors. So therefore, substituting the things here, the resultant electric field magnitude, the magnitude of resultant, it is under root of EA square, this is EA, 1 by 4 epsilon naught q by A square. So it's 1 by 4 pi epsilon naught q by A square whole square plus EB square, even this is also the same, it's 1 by 4 pi epsilon naught q by A square whole square plus 2 times EAEB, it's 1 by 4 pi epsilon naught q by A square times, again the same, this is whole square cos theta, whole square cos theta. Now, so the resultant electric field is equal to, all the terms are having same magnitude, I can take the common things out. So it's 1 by 4 pi epsilon naught q by A square common out, it is under root of, this has come out 1 plus even this has come out 1 plus this is 2 cos theta. So therefore, resultant electric field is 1 by 4 pi epsilon naught q by A square, it's 1 plus 1 under root of 2 plus 2 cos theta. So 2 bracket, it's 1 plus cos theta. Applying trigonometry, we know according to trigonometry 1 plus cos theta is equal to 2 cos square theta by 2. 2 cos square theta by 2. So substituting this, so E resultant is equal to 1 by 4 pi epsilon naught q by A square under root of 2 of 2 cos square theta by 2. So 2 into 2, it is 2 square. It's 2 square cos square under root. Removing the root and square. So the resultant electric field is 1 by 4 pi epsilon naught q by A square. It is 2 cos theta by 2. That is the resultant. Now the angle between the vectors is 60 degrees. Substituting 60 there. So the resultant electric field magnitude, it is 1 by 4 pi epsilon naught q by A square, it is 2 times cos angle 60 by 2, it is cos 30, root 3 by 2, 2 cancel. So 2 and 2 if I remove, so the final answer is root 3 of this is the resultant electric field. So root 3 q by 1 by 4 pi epsilon naught A square. This is the actual method of solving the electric field. But you know, you can even do it in a simpler manner. So I wanted to let you know all the different methods. So first, this is the actual method, A square plus B square plus 2AB cos theta. This is the first method. You can even do it in a simpler way also, right? I wanted to let you know all the things. So first, this is the actual method. If I put it in a simple form, let's understand this in a simple form also. So you better know all the methods. Whichever method you understand better and you remember better, you follow. So whichever method you like, you can use, right? This is the first thing, actual method of solving it. Now, so the resultant electric field is like this. In this one, we have a note in parallelogram law of vectors. Two vectors A bar, B bar, angle at an, two vectors A bar and B bar at an angle theta. So the resultant R is root of A square plus B square plus 2AB cos theta. But if A and B are of same magnitude, let's say P, then the resultant R can be written as 2P cos theta by 2. Direct step. First, I wanted to give you individually. I wanted to explain it elaborately. Then direct step, applying direct trick there. So if these two are of same magnitude, then the resultant you can simply write it as it is 2. If both are of same magnitude E, let's say now the magnitude of EA is equal to magnitude of EB is equal to E, then the resultant magnitude you can simply write as, according to the note from the Parallelogram law of vectors, it is 2E cos theta by 2 directly. How it is 2E cos theta by 2? I have derived. First substitute the individual things, take the common things, you get under root of 2 of 1 plus cos theta, apply trigonometry, then you got it as like this. So if you can remember the simple trick shortcut directly, then you can even apply it. If not, you better know first that, later you apply the trick. So it's 2 times E. E is the magnitude of either of the vectors, E and EB, either of them. So it's 1 by 4 pi epsilon naught Q by A square. It's Q by A square times cos of theta by 2. It's cos 60 by 2. So therefore magnitude of the resultant electric field is 2 by 1 by 4 pi epsilon naught Q by A square cos 60 by 2 cos 30. We know cos 30 is root 3 by 2, 2 cancel. So the magnitude of the resultant is root 3 Q by 4 pi epsilon naught A square. This is the result. So if the question was 3 identical charges of same magnitude and same nature, the identical charges are placed on the vertices of an equivalent triangle of side A. Right? There are different questions. First question we have taken was the resultant electric field at any of the vertex. Any of the vertex. Let's see. Let us consider as point C. So the resultant electric field at C, we know. So first step, the method is, first step, considering each charge as an isolated positive charge, find the electric field due to each charge separately. First charge due to A, so the electric field due to A, 1 by 4 epsilon Q by A square. Electric field due to B, 1 by 4 epsilon Q by A square. Then electric field due to C, since the point is C, the charge is at C itself, so we know a charge cannot produce field on itself. The intensity at that point where it is lying itself is 0. So the field due to the charge C at itself is 0. Now second step, applying principle of superposition. Resultant electric field is the vector sum of all the individual electric fields. EC is 0, so this is plus 0. So E and EB, 2 vectors. We know when there are 2 vectors, we can find the resultant, the magnitude of the resultant. The result vector can be evaluated from Parallelogram law of vectors. So the resultant is root of A square plus B square plus 2AB cos theta. So EA square plus EB square plus 2EAB cos theta. Actually, the method is substituting the individual values and evaluate. But since both are of same magnitude, we have a trick. We have a note in Parallelogram law of vectors where if 2 vectors are of same magnitude, P and P, then the resultant magnitude is simply 2P cos theta by 2. So if here we have observed magnitude of EA 1 by 4 epsilon Q by A square, this is also 1 by 4 epsilon Q by A square. Since the charges are of same magnitude and the distance is same, magnitudes of the fields are same. Let EA and EB have magnitude E each. Then according to the note, the resultant is 2P cos theta by 2. So the resultant is 2E cos theta by 2. E is the magnitude of either of the fields, EA or EB. It's 1 by 4 epsilon Q by A square cos the angle between the vectors. It is an equilateral triangle. Angle between the sides is 60 and the vertically opposite angle here. So therefore it is cos 60 by 2 cos 30 root 3 by 2. 2 to cancel the resultant fields like this. So if there are 3 identical charges placed on the vertices of an equilateral triangle, the resultant electric field has a magnitude 1 by 4 pi epsilon naught root 3 Q by A square. So sometimes he'll ask you, field due to each charge is E. Then if there are 3 charges, what is the resultant field? That is, for example, let's suppose these 2 are not existing, only A is existing. So only due to EA, the field is E. EA is E. Then in the presence of these three charges, what is the resultant field? Now if I evaluate, so there is another question. Another question. Field due to each charge is E. Then what will be the field when there are all the three the charges are existing? So the resultant field due to all the charges is, it is root 3 times of 1 by 4 pi epsilon naught q by a square. But 1 by 4 epsilon q by a square is the magnitude of E at A. So E resultant is root 3 times E. This is another question you can imagine. Resultant electric field is root 3 times. So when there are like charges, the resultant field here is root 3 times the field due to each charge. The question can be asked like this also. If each charge produces a field E at any of the vertex, then due to the presence of all the three charges, what would be the resultant electric field due to all the charges? The answer is root 3 times E. Magnitude, right? Thank you. So the magnitude of the resultant electric field intensity due to these charges is E, root 3. What will be the direction? The direction of the electric field. You see, this is the field due to one vector. This is the field due to another charge. The resultant, third is not existing, 0. So the resultant direction is like this. Now how is this? This is in the direction of the median of this equilateral triangle. Right? This is the median. Right? The direction of the resultant vector is in the direction of the median from the line extending from the center of the triangle to the vertex in this direction. It is along the angular bisector of these two vectors, or along the line extending from the median to the vertex. This is the direction of the resultant electric field. Same thing even if you find the field at point B also, then A will be producing a field like this, B will be producing a field like this. The direction of the field will be in this way, of same magnitude this way, right? Okay. So in this one, we have considered all the three charges to be of same magnitude and all are like charges. Now let's do it. If one of the charge is an unlike charge, if the charge at A is unlike charge, then what would be the electric field at the point C? So the question is like this. Now the question is, two equal and unlike charges are placed at two vertices of a equilateral triangle. Two equal and unlike charges are placed at, even if they are three also, it does not matter, because you are asked to find the field at the vertex. The field due to the charge at that point is 0. So that is already taught you. I wanted to let you know that even if the presence of the third charge at that point, the field will not exist. So the third charge, its presence does not matter. Now if there are two equal and unlike charges at the vertices of two vertices of equilateral triangle, what is the resultant electric field at the third vertex? Now this is the question. So the resultant electric field at the third vertex, C, is asking, right? Now I was telling you, the method is, first step, considering each charge as an individual. So the question says, if two equal and unlike charges are placed on the two vertices of equilateral triangle, what is the resultant electric field at the third vertex at this point? So I was telling you, the method is, first step, find the electric field due to each charge individually. Field due to A, field due to the charge at A, and field due to charge at B. Then second step, the resultant electric field is the vector sum of all the fields. So first step, let me find the electric field due to first charge A. Now we know, according to the definition of the electric field intensity, it is the force experienced by a unit positive test charge. So let me imagine a unit positive test charge, 1 coulomb test charge here. So charge, now first step, I have to find the field due to charge A at point A. Now charge at point A, it is a negative charge. Now this positive test charge will be attracted by this negative charge. So therefore the force experienced by the positive test charge due to this charge is, this is in this direction, it is EA. It is towards the charge EA like this. Magnitude of EA, field due to charge at A, it's 1 by 4 pi epsilon naught charge magnitude Q, distance is A, it's 1 by 4 pi epsilon Q by A square, right? Direction, since this is negative charge, it attracts the test charge. So the line of force is towards it. So the field is EA in this direction. Second, now consider the charge due to Q, field due to charge at Q, charge at B. Now this is positive charge. Now the field due to charge at B, this positive charge repels this positive test charge. So the field due to B, EB, so the EB mod this is. So EB is equal to same 1 by 4 pi epsilon naught, same magnitude Q, same distance A square, magnitude is same. But the direction here, since charge at B is positive, this positive test charge is repelled by the positive charge. So the field will be in this direction. So this is EB, this is EA, right? Now completing the parallelogram. So first step, find the fields individually, consider them as isolated charges. I have found the magnitude and I have taken the vectors also, direction. Second, the resultant electric field strength is given by, according to the principle of superposition, the resultant electric field strength is given as the vector sum of all the individual electric fields, E1 bar plus E2 bar plus E3 bar dot dot dot. So therefore, the resultant electric field is EA bar plus EB bar, since there are two charges. So even if there had been a charge at C, suppose the question reads 3 charges, like 3 charges positive, 3 charges Q each are on the vertex of equivalent triangle. Even if there had been a charge at C, then it will not produce any electric field due to itself at that point. So it does not matter whether there is any charge given here or not, and it even does not matter whether it is positive or negative also. So don't get diverted, don't get confused that there are field due to 2 charges or field when there are 3 charges. It does not matter, because the point of concentration, at the point of concentration, whether the charge is existing or not, it does not matter, right? So in the problem now, we have taken only 2, so therefore it is EA bar plus EB bar. We know the magnitude of the electric field. Magnitude of the electric field, we know these 2 vectors form 2 sides of a parallelogram. You have to find the resultant by the parallelogram law of vectors. If I consider these 2 as the 2 adjacent sides of a parallelogram, completing the parallelogram like this, 2 adjacent sides, then the diagonal passing to the point of intersection gives the resultant vector. So this gives the resultant vector, right? And magnitude of the resultant vector is given as root of A square plus B square plus 2AB cos theta, magnitude of the vector A and B. And the angle, vectors are EA, EB. What is the angle? Now in the equality triangle, all the sides are equal, all angles are equal. So each angle is 60 degrees. But our vectors are E and EB, angle between vectors is this one. This is the angle we need. But this is a straight line. Angle in a straight line is 180 degrees. Out of this 180 degrees, it is already 60 degrees. So the remaining angle here is 120 degrees. So the angle between the vectors is 120 degrees, EA and EB, right? So the angle theta is 120, our required angle. And I was just now telling you, when 2 vectors are of same magnitude, let EA mod EA is equal to mod EB, magnitude be equal to same magnitude. Applying a note in the parallelogram law of vectors, the note says if 2 vectors are of same magnitude P each, then the resultant magnitude is 2P cos theta by 2. So these 2 have same magnitude E each. You see the magnitude is same, 1 by 4 not Q by A square magnitude. Then the resultant is 2E cos theta by 2. Theta by 2. So therefore magnitude of the resultant is 2E. What is E? Either of the magnitude of A and B. It's 1 by 4 pi epsilon naught Q by A square times cos of Now the angle between these two vectors is 120 degrees. It's 120 degrees pi 2. So therefore magnitude of the resultant is 2 times 1 by 4 pi epsilon naught q by a square. Cos 120 by 2 is cos 60. According to trigonometry, cos 60 is 1 by 2, 2 to cancel. So therefore the magnitude of the resultant vector mod E is 1 by 4 pi epsilon naught q by a square. This is the magnitude. The magnitude of the resultant electric field due to two unlike charges. Two unlike and equal and opposite charges at the third vertex is 1 by 4 naught q by a square. And the direction is the angular bisector of these two charges. The angular bisector of these two charges. To be very specific, going keen into it, this will be parallel to the line joining the charges. Actually, getting into the geometry of it, this vector will be parallel to the line joining the charges, and the direction is in the direction extending from plus to minus. Right? So you will be learning about more keenly about this in the future of this thing. But according to geometry, this will be parallel to the line joining the two charges and will be directed from plus to minus like this. Okay, right. Magnitude 1 by 4 naught q by a square. Now if the same question is extended, if the same question is revealed like this, if question says like this, two equal and opposite charges plus q and minus q are on the vertex of a equilateral triangle, then if the field due to each charge is of magnitude E, there are two equal and opposite charges, field due to each charge is E, then what is the magnitude of the resultant field due to these two charges? Now field due to each charge, only one charge. This is equilateral triangle of side A. Field due to each charge is 1 by 4 pi epsilon q by a square. Charge is q, distance is a. So each charge 1 by 4 pi epsilon q by a square. If I consider both the charges, what is the resultant electric field at this point? So when there are two equal and unlike charges, the resultant electric field at these 2 points, 1 by 4 pi epsilon q by a square. Same 1 by 4 pi epsilon q by a square. So the resultant field, even if there are two charges, is same as the field due to individual charge. A very beautiful question. He says, if the field due to each charge at the third vertex is E, then what is the resultant electric field due to the combination of these two charges? Two charges taking them together, what is the result? The answer is same magnitude C, E. Very tricky question. We actually feel, if field due to each charge is E, then field due to the combination would be something E, some number of times E, maybe twice or thrice, something like that. We will be imagining something. But the trick is, it is the same E, because it is a vector sum. Very beautiful question. Earlier, just now we have taken, right, if these two had been like charges. Now another question. Three identical charges are placed on the vertex of equilateral triangle. Three identical charges are placed on the vertex of equilateral triangle of side A. Right? This is the point A, C, B and C. When all the charges are like, same charges, same nature, then the resultant electric field at the vertex is E1. When all the charges are like charges, the resultant electric field at one vertex is E1. If any of the other, at the point of concentration here is E1, other than the point, if any of the other two charges unlike, first, if all are same magnitude and like charges, then the electric field at any vertex is E1. The question continues. If any of the other two charges at other two vertices other than the point where the electric field is considered, if any of these two is unlike, then the electric field is E2. Then what is the ratio of E1 and E2? Very beautiful combination. Now the questions actually, first a simple question, then another simple question. Usually in entrance examination, the question will be a combination of two simple things, two ideologies, two concepts, two theories. So that way he combines. First he says, if these two charges are like charges, then the resultant field, electric field at the third vertex is E1. If one of these two is unlike, then the resultant electric field is E2. What is the ratio? We have evaluated when these two are like charges, or these two are like, then the electric field at the third vertex, we have found it as root 3 times the field due to each charge. We have evaluated the question earlier. If each charge produces a field E, then when these two are like charges, same nature, same magnitude, then the resultant electric field is root 3E. According to the problem, it is E1. Now, if one of the charge is unlike this question, minus q plus q, then the resultant electric field 1 by 4 epsilon q by a square, it is same as the field due to either of the charges. So this is equal to E. Now what is the ratio? Ratio is E1 by E2 is root 3 is to 1. A very beautiful question which you can expect in the next entrance examination. It's a combination of two problems like this, right? So when there are two charges, first two equal like charges, then the field at the third vertex is E1. Two equal unlike charges, field at the third vertex is E2. Then the ratio of E1 to E2 is root 3 is to 1. Very beautiful question. So let us, according to this one, so when two equal and opposite charges, when placed at two vertices, then the resultant electric field at the third vertex. Method, first step, find the field due to each charge separately, E1 and E2. Field due to A, magnitude, direction. Field due to B, magnitude, direction, EA, EB. Then vector sum, according to the principle of superposition, vector sum, EA bar plus EB bar. It's root of EA square plus EB square plus 2EAB cos theta. Applying the note, it's 2E cos theta by 2. Substituting, the answer is this. Right? Thank you.